kinematics, or motion along a straight line. In order to describe the motion of an object, you must first be able to describe its position, where it is at any particular time. More precisely, you need to specify its position relative to a convenience reference frame. So we recall reference frame as any object or point from which motion is determined. Earth is often used as a reference frame, and we often describe the position of an object as it relates to stationary objects in that reference frame. For example, a rocket launch would be described in terms of the position of the rocket with respect to the Earth as a whole, while a professor's position could be described in terms of where he is in relation to the nearby whiteboard. In other cases, we use reference frames that are not stationary but are in motion relative to the Earth. To describe the position of a person in an airplane, for example, we use the airplane, not the Earth, as the reference frame. We've learned that the most fundamental physical quantities are defined by how they are measured. This is the case with time. Every measurement of time involves measuring a change in some physical quantity. It may be a number on a digital clock, a heartbeat, or the position of the sun in the sky. In physics, the definition of time is simple. Time is change, or the interval over which change occurs. It is impossible to know that time has passed unless something changes. The amount of time or change is calibrated by comparison with a standard. The SI unit for time is the second. We might, for example, observe that a certain pendulum makes one full swing every 0.75 seconds. We could then use the pendulum to measure time by counting its swings, or, of course, by connecting the pendulum to a clock mechanism that registers time on a dial. This allows us to not only measure the amount of time, but also to determine a sequence of events. How does time relate to motion? We are usually interested in elapsed time for a particular motion, such as how long it takes an airplane passenger to get from his seat to the back of the plane. To find elapsed time, we note the time at the beginning and end of the motion and subtract the two. For example, a lecture may start at 8 a.m. and end at 9 a.m. so that the elapsed time would be 60 minutes. Elapsed time t is the difference between the ending time and beginning time. Delta t is equals to t minus t naught, where delta t is the change in time or elapsed time. T, or the t final, is the time at the end of the motion, and t naught is the time at the beginning of the motion. As usual, the delta symbol means the change in the quantity that follows. Life is simpler if the beginning time t naught is taken to be 0, as when we use a stopwatch. If we were using a stopwatch, it would simply read 0 at the start of the lecture and 60 minutes at the end. If t naught is equals to 0, then t time is equals to the final time or your total time. For simplicity's sake, motion starts at time equal to 0. The symbol t is used for elapsed time unless otherwise specified. Let's talk about distance versus displacement. What is the difference between them? We answer this question by first putting an emphasis on describing the motion of an object. In order to describe the motion of an object, you must first be able to describe its position, where it is at any particular time. More precisely, you need to specify its position relative to a convenient reference frame. If an object moves relative to a reference frame, for example, if a professor moves to the right relative to a whiteboard, or a passenger moves toward the rear of an airplane, then the object's position changes. This change in position is known as displacement. The word displacement implies that an object has moved or has been displaced. Displacement is the change in position of an object. Delta x is equals to x final minus x naught, where delta x is the change in position of an object, x is the final position, and x naught is the initial position. Say we identify 2 points by which the professor travels from an initial position x0 of 1.5 meters to a final position equal to 3.5 meters. So the change in position or the displacement is equals to delta x equals x minus x0. Our final position is equals to 3.5 meters while our initial position is equals to 1.5 meters. This will give us a total displacement of positive 2.0 meters. Here we can say, for example, a passenger in an airplane going towards the rear of an airplane, if we say we measure the final position to be 2.0 meters and the initial position x0 to be 6.0 meters, we can calculate for the total displacement or the displacement or change in position as delta x equals to x minus x0. In this case, we have delta x is equals to final position, which is 2.0 meter, minus initial position, which is 6.0 meter. This will give us a negative 4.0 meter. The negative sign indicates that the passenger traveled in the opposite direction or on the negative side of our coordinate. Distance is identified to be the magnitude or size of displacement between two positions. So we note that the distance is the total length of the path traveled between two positions. Distance has no direction and thus no sign, whereas displacement is defined by both direction and magnitude. Let's talk about speed and velocity. In everyday language, most people use the terms speed and velocity interchangeably. In physics, however, they do not have the same meaning, and they are distinct concepts. One major difference is that speed has no direction. Thus, speed is a scalar quantity. Velocity, on the other hand, is probably the same as its scientific definition. You know that if you have a large displacement in a small amount of time, you have a large velocity, and that velocity has units of distance divided by time, such as kilometers per hour or miles per hour. When we say average velocity, it refers to the displacement or change in position divided by the time of travel. So we can say that delta x is equals to final position minus initial position x minus x0 divided by delta time or elapsed time, or equal to time final minus time initial. Here, average v is the average velocity, where v bar is the average velocity, delta x is the change in position or your displacement, and delta t is the elapsed time. If the starting time t0 is taken to be 0, then the average velocity is simply v bar is equals to delta x divided by delta t. Notice that this definition indicates that velocity is a vector because displacement is a vector. It has both magnitude and direction. The SI unit for velocity is meters per second, but many other units such as kilometers per hour, miles per hour, also written as mph, and centimeters per second are in common use. Suppose, for example, an airplane passenger took 5 seconds to move -4 meters. The negative sign indicates that displacement is toward the back of the plane. His average velocity would be v bar, or average velocity, is equals to delta x divided by the time. So we have -4 meters as your displacement divided by 5 seconds. The answer here is -0.8 meters per second. The minus sign indicates the average velocity is also toward the rear of the plane. The average velocity of an object does not tell us anything about what happens to it between the starting point and ending point. However, for example, we cannot tell from average velocity whether the airplane passenger stops momentarily or backs up before he goes to the back of the plane. To get more details, we must consider small segments of the trip over small time intervals. The smaller the time intervals considered in a motion, the more detailed the information. When we carry this process to its logical conclusion, we are left with an infinitesimally small interval. Over such an interval, the average velocity becomes the instantaneous velocity, or the velocity at a specific instant. A car's speedometer, for example, shows the magnitude, but not the direction, of the instantaneous velocity of the car. Instantaneous velocity v is the average velocity at a specific instant in time, or over an infinitesimally small time interval. Mathematically, finding instantaneous velocity v at a precise instant time can involve taking a limit, wherein instantaneous velocity is equals to delta x divided by delta t. As time approaches 0, we take the derivative of x in respect to time. However, under many circumstances, we can find precise values for instantaneous velocity without calculus.